okay, Dr. Mink. We'll find somewhere for you.
Well,
Find you a job.
well, find me something for you.
We'll send in stuff.
I appreciate that. Looking out for me. Okay, lecture 9. I have good and bad news. Well, I think it's good news both ways, but I imagine I'll get varying responses from you that we have. Next week is interesting. For one, we have our February break. So guess what happens on Friday of next week? We don't have class on Friday of next week. Nobody has class on Friday of next week. But what do we have Wednesday of next week? We celebrate, yes. So this week will be our end of tension members, although, you know, it's also the week where we put everything together. We'll review Monday, exam on Wednesday, okay? Sound good? No class on Friday. And when we come back, we foray into the land of bolts when we come back from our February break. How did the last analysis homework go? That went well? How did the shear lag factor go? What was the shear lag factor, by the way? There you go. Okay. All right. Today what we're going to do is design. We're going to do design today. We're going to do design on Wednesday. Okay? So today what we need to do is just sort of, I don't know, like, go through the process. Go through it step by step. I'm getting ahead of myself. I had a question right before class, and I wanted to address it. Question was, for your manual, what pages should you tab for the first exam? And I don't really have a lot. First off, I would say the shapes, and I wouldn't tab all of them. What I would tab are the W shapes, the channels, the angles, and the WTs. That's probably what I would tab. I wouldn't have a tab for every single shape. Like maybe as a practicing engineer, I might throw another one for hollow structural sections, but no more. I mean, because there's, what, 23, 24 tables, but they're sequential, right? So that's enough, I think, for navigating steel design. I would put a tab here because you need that for FY and FU. And I would put a tab here for your shear lag factors. Given the fact that I'm going to let you have a formula sheet on the exam, I don't think that there's anything beyond this that you couldn't just put on your formula sheet. So I think that's enough. So I'll leave this up here. Okay. Yeah, so the shapes, FY and FU, and then this. So as we get to later exams, we'll add more to it. Okay? Sound good? All right. Okay, so let's talk about design. Let's see, maybe if I click the slideshow. There we go. Okay. So ultimately what we're doing again is LRFD. You've seen this slide before, so I'm not really going to spend too much time on it. For tension member limit states, right now we only have 2. So we have 3 limit states overall. We have gross section yielding, net section fracture, and slenderness. Okay? We'll add a 4th. We'll add block shear rupture later. That'll be Friday. That'll be our last lecture before the exam. But for today and Wednesday, we're just dealing with these 2. So I've shown you a little bit of this today. I've shown you a little bit of these slides. I showed you this on Friday. But I want to dig into it in a little bit more detail today. I want to go through the full step-by-step process for designing a tension member. We will exercise this today with an example. Okay. All right, so let's go through some ground rules. And I really went fast with this stuff on Friday, so I want to take my time. So what do I mean by design? Well, maybe what I should do is start by saying, what do I mean by analysis? Okay. What do I mean by analysis? What I mean is I give you details about a member, and your job is to assess the member's performance. Here is a W10 by 49 with 3/4 inch diameter bolts, spaced 3 inches on center. It is subjected to a dead load of this, live load of that. How is it going to perform? So you factor the loads, gross section yielding, net section fracture, compare them, compute efficiencies, slenderness check, all that. That is analysis, okay? If you want to call it assessment, that's fine. To segregate it from what we did last semester in CE 312, that's fine. But that's what we mean in here when we say tension member analysis or analysis of any component in a building, bridge, structure, what have you. What do I mean by design? Design means you don't have the details about the member, or maybe you have some details, but your goal is to select a member. To select a member out of that big gold book that can safely resist those loads, okay? And I imagine that you all would like to have some sort of way of doing that besides tearing out all of the shapes, taping them to the wall, and getting a few darts and throwing them at the wall, and whichever member it lands on, that's your choice. I imagine you want some sort of way of navigating that. Well, that's what we're going to talk about. Before we do that, let's establish some ground rules. So, in this class, we will always select the lightest member possible. And I want to be clear that generally that's the case in the real world, that you're wanting to select, you know, if you were given a problem between two choices, select the one that's lightest. That may not always be the case in a real world structure, so I'll give you an example of what I mean. How many floor beams do you think are in this building? Quite a lot, right? There's hundreds of floor beams in this building. And so maybe designing each beam individually would result in hundreds of different designs that would make the contractor's life a nightmare. Instead, what we'll do is we'll pick a restricted number of sections and just repeat them throughout the building. Does that mean that there are some beams that are quote-unquote over-designed? Probably. But does it ultimately mean in a faster, more efficient construction process? Yes. Okay? So you got to think about that too. We're not really going to worry about that in here, but I throw that out there just to give you a little bit of that real-world taste. The other thing is, these problems will always contain some sort of constraint to ensure that we're all going to get at the same answer, okay? So, I have no problem if you work on this with your friends, working on homeworks with your friends, not on exams, but if you and your friend are getting different answers, somebody's doing something wrong, okay? That's the case. Okay. Like I said, we're going to try and avoid throwing darts at the wall and just picking a shape at random. So let's see if we can hone in on a shape. And what that means is, for example, if you open up the table for angles, okay, there are numerical properties for those angles that we would like to be able to use to select members. In other words, could I solve for a necessary radius of gyration and then pick a member that has a radius of gyration at least that, if not bigger? Yes. Okay? So that's what we want to try and do. So right now we have 3 limit states to consider. The fourth one, block shear rupture, we're not really going to design for block shear rupture. Block shear rupture is something we're just going to check later. Okay? So that, but we'll deal with that later. But right now we have gross section yielding, net section fracture, slenderness. So let's take these one at a time and see if I can solve for the necessary properties that are listed in Table 1, or in Part 1 of the manual. Can I solve for those properties that'll help me pick a section? So with gross section yielding, if we look at our expression, we say resistance is greater than or equal to loads. The loads are just the factored loads, okay, and the resistance, according to that limit state, is 0.9 FYAG. So if I know what the grade of steel is, I can divide both sides by 0.9 FY, and I can solve for this. So in other words, I can calculate what I'm calling a gross area for design, and I can say, all right, let's say the gross area for design is 6.2 square inches. pick a member that has a gross area at least that, if not bigger, okay? Then I'll know I meet that limit state, okay? What about slenderness? Well, slenderness is just as easy, right? We know our slenderness has to be greater than or less than or equal to 300. There's a typo. Whoopsie. That's a typo. The slenderness needs to be less than or equal to 300. L over R needs to be less than or equal to 300. So what I can do is I can solve for R, multiply both sides by R, divide both sides by 300, and I get a radius of gyration for design purposes of L over 300. So essentially what I'm doing is I'm figuring out these design expressions, these design parameters that'll help me look up sections. Okay? Everybody with me so far? Now, which limit state am I missing? I got gross section yielding, slenderness, what's missing? Net section fracture. So let's talk about net section fracture. That one becomes a little bit trickier, okay? Because our design expression is 0.75 FU times the net area times U. Well, first off, there's a problem with the net area because the net area is a function of the thickness of the hole, which we don't know what that is if we're in design mode, right? We don't have any idea what the thickness of the plate is because we don't know what the plate is. We haven't picked it yet, okay? That's the problem with net area. What about shear lag? Well, we have no idea what the shear lag factor looks like because the shear lag factor, that's a function of the member geometry, of the connection geometry. We don't know what that is in the beginning either. Excuse me. So, what do? Okay? In order to handle this, we have to make an assumption. We have to guess something. Okay? And what I'm going to guess, okay, is this. Okay? So here's our, like, how do we calculate net section fracture? We say 0.75 FU AN times U, right? That's how we calculate net section fracture, right? Okay? What I'm going to do is I'm going to say, instead of net area times U, instead of that, what I'm going to do is say that this quantity is about 75% of the gross area. Okay? That is a guess. Just, I'm being totally candid here. That is a guess. That is an educated guess, but it is a guess. Okay? So we got to guess something. This is a reasonable assumption. And if you don't believe it's a reasonable assumption, just take a look at all the homeworks that we've done so far. Calculate net area times U and calculate 0.75 times the gross area. They're not that far apart, okay? They're not the same, but, you know, they're close. So therefore, if we have that the resistance is greater than or equal to the loads, I am replacing this quantity with 75% of the gross area, and now I'm just going to solve for the gross area, and I get this. So if you look at this fraction, why is there a 0.75 squared? Well, one of those 0.75s comes from the phi value. The other one comes from the assumption for the relationship between gross area and effective net area. Okay? Does that make sense? Again, it's a guess. It's an educated guess, but it's a guess. So now what we're going to do is combine these two gross area expressions. Okay? So let me show you how we're going to do that. So let's assume that we computed, let's do the math in our head. Let's assume that we computed this and this. Okay? If you're picking members, if you had a design value, or a gross area design 1 and a gross area design 2, which value would you use as your North Star for picking a member? The smaller one or the bigger one? Small. Well, let me ask it this way. So, let's say according to gross section yielding, you need 9 square inches. According to net section fracture, you need 10 square inches. Are you going to pick a member that has 9.5 square inches? No, you're going to pick a member based on the bigger of these two, right? And if you're going to pick a member based on the bigger of these two expressions, same numerator, what does that mean for the denominator? use the smaller denominator. Does that make sense? So if I have 8 divided by 2, 8 divided by 3, which is the larger value? It's 8 divided by 2 because it's the smaller numerator. Does that make sense? So instead of calculating gross area design 1, gross area design 2 separately, we're just going to calculate this as the minimum of these two. Does that make sense? Okay. So with that, I think we've got enough data to develop a step-by-step process, okay? And don't worry, this is going to show up on this slide again, don't worry. So let's go through a step-by-step process. And to be clear, I don't really think there's anything hyper-inventive about this process. I think you probably could come up with this process yourself right now. If you were designing a member to withstand a given set of loads, what do you think is the first thing you need to do? Like if I give you a member and I say, I want you to design it for a dead load of 80 kips and a live load of 150 kips, what do you think the first thing you need to do is? How about factor the loads? That's the first thing you're going to have to do, right? Now, I put this in a separate step because, for one, like let's think of the 3 ways I can probably give you this. I could just give you the factored load. I could just say, have the factored load is 500 kips, move on. That's one way of doing it. Another way of doing it is give you a dead load of 50 kips, a live load of 100 kips, and let you factor them. That's another way. A third way of doing it would be what I did to you on the last homework, which is I give you a structure. You must analyze that structure and then factor it. Either way, we need to know what we're designing for before we can begin design, right? Once we do that, let's compute our design parameters, okay? Right now we have 2 of them, the gross area design and the radius of gyration for design, okay? Which is going to be, for gross area, the factored load divided by the minimum of 90% of FY, or FU. Oh man, I had another typo. That's what happens when you update all your slides. That's FU. Whoopsie. So 0.75 FU, 0.75 squared times FU, and then the radius of gyration is just L over 300. Okay. Now what we're going to do is we're going to use those values, pick a member out of the manual. Are we done at that point? See, I say no because this is a guess. We need to check the member. We need to analyze the trial shape to verify that it's actually going to work. And in particular, we're looking at the net section fracture limit statement, because that's the one that's really a function of the guessing. And then finally, we need to summarize the results. Probably not a bad idea to compute the efficiency of the design, and as for why, I'll talk about that here in a bit. Okay? Okay. I'll update these slides on Blackboard, by the way, to correct those couple of little typos of mine. You want me to leave it up here for a second, or is everybody good? 1 second, that's fine. All right. Before we get into design, I have a couple notes I want to throw at you, okay? First off, step 4 is very important, okay? Again, you need to keep in mind that in order to pick that shape, it is a trial shape. We don't know whether or not that shape's going to work. In fact, it is possible that you select a shape and then you check that shape and it doesn't work. It is very possible. When that happens, just go to the next heaviest section in the manual and repeat, okay? Which is one of the reasons why on Wednesday, we're going to look at, since a lot of these calculations are repetitive, breaking out our old friend Microsoft Excel and seeing if Excel can make our life a little easier in that regards, okay? So we're going to talk about that on Wednesday. All right, in step 5, I mentioned the term efficiency, okay? A good rule of thumb is that if efficiency is 90% or better, then you're good. I will, so for example, let's say you're doing a homework problem and the efficiency is 91%. And it just so happens that if you were to happen to check the next slightest member, you get an efficiency of 98%. I am not going to expect you to be clairvoyant in that regard, okay? So if you do the problem properly and you get 90% or better for a tension member, you're going to get full credit, okay? Now, the other thing I'll tell you is that efficiency does start to mean less when we're talking about columns, when we're talking about beams, when we're talking about bolted and welded connections, and I'll just say we'll talk about that later. But in tension members, this is probably the one area where efficiency really is a good guide. If you have a really low efficiency, go to the next slightest section and check it. So like if you compute your efficiency for a tension member and you get like 70%, go to the next one and check it, okay? Because chances are it'll work. And again, the thing with efficiency is you want to get as close to 100% as possible without going over. Okay? If you go over, the loads are bigger than the resistances and the member is unsafe. Okay? Does that make sense? Okay. So this is going to be our our problem for today. Okay. Let's look at our member, or our problem for today. So we're going to select the most economical channel. This is a C shape, okay, that we can out of A36 steel to be used as a tension member. The tension member is 21 foot long. So we do know about our connection scheme, but we don't know what channel we're going to use to support these loads. The loads themselves are 100 kips of dead load, 120 kips of live load. Those are service loads, so we need to factor them. These are 3/4 inch diameter bolts. Let's see. Now, one of the things about channels is that there aren't very many of them, okay? So, because there aren't very many of them, we're going to arrive at the same answer as a class. We're not going to get to a point where you get a different answer than you and you get a different answer than her. That's not going to happen. We're all going to arrive at the same answer. Okay. All right. Okay. Sorry, still getting over my sinus infection. Gotta love it. I do want to give everybody a sec to jot some of this down because I do want your participation on this. This is important. Okay. All right, is everybody good? All right. So, let's see if we can just highlight some values that we know are going to be constant. So, for example, what information can I glean from the fact that the bolt diameter is 3/4 of an inch? There we go. What about the fact that we're dealing with A36 steel? Which, by the way, is one of the most common material grades for channels. So, what does that tell us?
XY is 36 KSI.
And where did you get that?
Table 2-4.
There we go. And FU.
Is 58 KSI.
There we go. Two other things that we can figure out just right off the bat. We know that the member length is 21 feet. How many inches is that? 20 feet is 240 inches. So another 12 inches is 252. Did I do that right? And what's our connection length going to be? 7 inches. Okay. Like, let's just go and get some of that stuff out of the way so that when we start doing our problem, we've already got that figured out. Okay, what was step 1? The factored load. Okay, so let's see. What service loads is this member going to be subjected to? There was a dead load. What else? Nothing else, right? What were the dead and live loads? What? So what we'll do is we'll evaluate LC1. Which I think I can do that one in my head. And LC2. This one I might need some help on. And what do we get for that? 312. Do I have a second? Okay, so step 1 said that PU is 312. Is that what step 1 said? Okay. And again, like, I'm teaching you all, so I'm trying to number the steps in a way that, you know, makes sense. But I mean, is there really anything magic about this first step? You know, I mean, you kind of need a factored load to be able to design. Okay, should be pretty straightforward. Okay. All right, step 2. That's going to be our design expressions. Okay, so I'm going to need some help, okay? What is 0.9 Fy? Okay, now what is 0.75 squared Fu? $32.62. Okay. So therefore, if I write this out, which is the minimum? The 0.9 Fy, which is 32.4. So I'm basically going to take 312 over that. What am I going to get? Okay. All right. What about our design? That's going to be LR 300, which we already did that. That was 252 over 300. So what are we going to get here? 0 point something. Make sense? So now we get our that. Okay. Before I open the manual up here, let me take a step back. Does this make sense? Does this make sense? Anybody have any questions on this?
I have one question.
Yes.
With the LC1 and LC2, where does those equations come
Those are just our load combos for LRFD.
from? Okay.
That's just like the 1.4 dead, 1.2.
Be the same?
Yeah, they're always going to be the same. Yep. No problem. Everybody else good? Okay. So, all right. So we're picking a channel, right? So let's go to okay, let's go here. All right. Let me zoom out a little bit. Okay. Now let me just make a couple points here. All right, let's just, for the sake of discussion, look at the C9x20. Would that work? You're shaking your head no. Why?
The area's not enough.
The area is too small. The area is 5.87. We need an area of at least this, right? Okay? Now, but it's not just the area. We have to go to the next page. It's like if we go to that section, would it work here? Well, let's see. Here's our radius of gyration in the x-axis. Here's our radius of gyration in the y. Would it work there too? No, because RY is 0.64. That's too small, right? Does that make sense? So what I want you to do is I want you to tell me what is the smallest shape that you can find that has a gross area of at least this and a radius of gyration of at least this. And we're looking for the lightest shape. So try a C something by something.
C15 by 33.5.
Okay. So obviously, based on our gross area, nothing down here is going to work. Like we got to start here, right? Okay. So try a C15 by 33.9. Is it going to work on the radius of gyration side? Let's see. Let's see, here's Rx. Here's Ry. So Rx is 5.61, Ry is 0.901. Right? So it's not the X bar, it's this one, 0.901. This is 0.84, so it just works, right? So is this a reasonable candidate to evaluate? Yes, it is. So our answer for step 3 is this is what we're going to try. Keyword is try. It might not work. I have no idea. Because we made some guesses to get here. Okay, so let's see. So we'll say so here's what before we turn away and start doing our analysis, if we're going to analyze this member, what are some relevant values that we'll need? Well, let me walk you through this. First off, that's obviously a value we're going to need, right? What's another one? Rmin, which in this case is Ry, which is 0.901. What else? What else are we going to need? If we're going to analyze this, let's go back to the problem. Let's go back up top. What are we going to need?
Web thickness.
The web thickness. Why the web thickness?
That's where the bolts are.
That's for the net area. That's where the bolts are going through. What other property are we going to need? Think further ahead. X bar. So the web thickness is what?
0.40.
And what about X bar? 0.788. Okay. So, now we have a shape. We have our properties for this shape. We need to verify. So what do we need to do? We need to analyze it. So, we could do gross section yielding, net section fracture slenderness. In order to do our limit states at the end, we need all of our properties, which means we need to start out, now that we have a shape, we can start out with computing the net area, right? What is the net area? How am I going to compute this? What's the formula going to be? The net area equals the gross area minus what?
DET.
All right, hold on. Let's see. So gross area minus DET. Am I missing something? Well, I know, but okay. Let's do this. All right. Let's do it like this. Let's just write our governing expression. Okay. Do we have any stagger in this connection? No, there's no stagger. I guess my question is, how many of those? Two. There's two bolt holes. So my expression, and what's the thickness, by the way? But it's the thickness of the web. That's sort of what I was getting at, is that our net area is going to be the gross area minus 2 diameter times the thickness of the web, which is going to be... Now, here's a question. What's my gross area? 10 square inches. It's not this. This is a parameter that we computed solely for the means of picking a trial shape. Once we get a trial shape, we ignore those two parameters. They don't mean anything anymore. Okay? What matters is the evaluation of the member at hand. And what is that? 9.3 inches squared. Do I have a second?
Yeah.
All right. Shear lag. Are there any, what cases are going to apply for shear lag? Is it going to be a case 1 or case 2? 2, obviously. Do any of the cases 3 through 8 apply? No, right? Case 7 is for W shapes, case 8 is for angles. This is a channel. What is my X bar, by the way? Okay. So what is that going to be? We'll say 3 decimal places. 0.887. Okay. So now can I start computing strengths? I've got everything I need now, right? Because I've got this. And again, actual gross area. Ignore our design parameters. They don't matter anymore because now we have a shape that we're actually evaluating. And then for NSF, what do we get for these? What is GSY going to be? 324. Oh, I don't know what happened there. What about the NSF? What is that going to be?
358.82.
358.8.
Yeah.
Second on that? So between these, what's my capacity? 324 kips. So let's do this. What does that mean? What does that mean in terms of the evaluation of a C15 by 33.9 as a potential option for this tension member? Is it going to work or is it not going to work? It'll work. Why? Because it's bigger than what? Bigger than the load, right? So that means it's going to work. So let's do a quick summary. Like, it'll work, but how well will it work? Well, let's see. how do we evaluate how well this works? Calculate an efficiency. And what is the efficiency?
96%.
Say it again.
96%.
96.0?
0.2.
0.2. All right. There's another thing that we have yet to formally compute. That's L over R. Let's just go ahead and do that just to make sure we're all comfortable here. So L was 252 inches. What was R min? Okay, and what is that? So 279.7? Bless you. Bless you. So, are we good? So, I guess my question is, what's the answer?
Channel 15, 33.9.
That's the answer. Use a, so instead of trying a C 15 by 33.9, the answer is that's the answer. Boom. Done. That's it. That's all there is to it. What do you think? Yes.
And the L over R that you calculated, it's never going to be over 300 because of how you started the problem?
Yes, that's a good point, yes. And so I usually kind of like doing it just to make sure that you didn't look up the wrong value or you didn't have a calculator glitch earlier in the problem. But assuming no calculator errors, you're right, it'll never be over. Now, hold on. So for your homework, I want you to here's the thing I want you to pay attention to. I want you to select the most economical W12s, okay? So a W12 by something, not a W10, not a W8, a W12, okay? Other than that, I think you'll find that the problem's fairly straightforward, okay? What we're going to do on Wednesday is we're going to start to ask, what if I open this up a little bit? What if I said, don't give me the best W12, just give me the best W section? There's a lot more math, but I think what you're probably seeing is it's just a lot of the same calculations over and over and over again, right? Which makes the use of Excel very, very nice, okay? So this is a perfect assignment to do this due Wednesday, so that when you come back on Wednesday, the spreadsheet stuff will be a lot smoother, all right? I'll pull up the code one more time. That's all I got.